to my today's session of electromagnetic field. Myself Dr. Sayanti Chatterjee, Associate Professor of Department of Electrical and Electronics Engineering, IARE, Hyderabad. Today we are discuss definition and important some definition and terminology from the last unit, that is the Faraday's law and the wave equation. So before starting, we will discuss that the COs, what are the course outcome. The first course outcome of this section is we can state the Faraday's law of electromagnetic induction and note the nature of the EMF induced in the coil for fixed and variable fields. Its Bloom taxonomy is remembered. CO12 is list out the differential and integral forms of Maxwell's equations in time-varying fields and time-varying with the harmonically with time, obtaining numerical solutions of complex engineering problems. And last one is the make use of the Maxwell's equations to produce wave equation for the free space insulators, conductors for propagation of electromagnetic waves. So first we will start with the time varying electromagnetic field. What is the meaning of time varying electromagnetic field? Already we have discussed about the magnetic field before. So what is field? Field means the area where we can feel some force. So field is basically two types we have discussed in the previous lectures. So field is just a quick revision. Field is basically two types in electricity. One is the electric field and another one is known as the magnetic field. And sometimes when we gives the current to an electric material, it turns or like some iron, it will changes into the magnet, and the interaction of these two will create a new one which is known as the electromagnetic field. So electromagnetic field, again we can divide the electromagnetic field into two types. One is the constant electromagnetic field, which is basically the unidirectional current or DC, or another one is the variable current or AC, which is known as the time varying. So today our question is how time varying fields are developed. You can see the case of the generating of time varying field is the cause of the electromagnetism. So time varying fields are produced due to the accelerated changes of time varying current. You can see the green one. Okay, you can see that the time varying fields are produced due to the accelerated changes in the time varying currents. The time varying field is produced by a time varying magnetic field, and a time varying magnetic field is produced by a time varying electric field. Already we have discussed these two important points. You can see the green one is the time varying current. When the time varying current is changing, it will create the flux which is time varying, and as a result it will create the time varying field. The concept was first experimentally introduced by the Michael Faraday, and it was theoretically introduced by the James Clerk Maxwell. So these two persons are known as the father of the electromagnetism. Next question. State the Faraday's law of electromagnetic induction. So what is the Faraday's law? Faraday's law is basically, there are basically two Faraday's law, Faraday's first law and Faraday's second law. What is the Faraday's first law? Any change in magnetic field of a coil of wire will cause an EMF to be induced in the coil. The EMF induced called the induced EMF, and if the circuit is closed, the current will also circulate to flow, and this current is known as the induced current. What does it mean? So if there is a time varying field, you can see here the green one is the time varying current, and as a result, you can see this is the time varying current, and as a result the blue one is the time varying field. Now if it is changing, it will create some magnetic field. It will create some magnetic field, and this magnetic field is also time varying in nature. We can write EMF induced is equal to rate of change of flux d phi by dt. So how we, and if the circuit is closed, so as EMF is the voltage source, current will start to move, and this current is known as the induced current. Now how we can change the magnetic field? First one, by moving the magnets towards or away from the coil. You can see if there is some coil, we can change the magnet towards or away from the coil. Say if this is a constant magnetic field and we are giving a conductor in it, if we change the field, what is the meaning of field? This is the north pole and this is the south pole. If we increase the distance between north pole and south pole, the field strength will decrease. If we bring the north pole and south pole closer, it will increase. So by changing the field, by changing the magnets, we can change the magnetic field. Number 2, by moving the coil into or out the magnetic field. We know this is the working principle of any motor, that if there is any magnetic field and it is the working principle of the generator, that if this is the magnetic field, if we want to move using a prime mover, this one, it will create a time varying magnetic field. By changing the area of coil placed in the magnetic field. If we want to change the north pole and south pole in a proper axis, we can get a time varying field. Say north pole and south pole is here. If we change the north pole here and south pole here, the field direction will also change. And by rotating the coil relative to the magnet. That is the working principle of the generator. So if there is, first law says, if there is a change of magnetic field, it will induce some EMF. What is the second law? It states that the magnitude of the EMF induced in the coil is equal to the rate of change of flux linkage with the coil. As we have discussed, E is equal to N d phi by dt. Rate of change of flux d phi by dt. And the flux linkage of the coil is the product of the number of turns of the coil and flux associated with the coil. If there are n number of turns, we can write E equals to N d phi by dt. So if we write it in one line, E is directly proportional to d phi dt and E is equal to N d phi dt. Already we have discussed. And third, next one, state the Lenz law of electromagnetic induction. So you can see the Lenz law is also known as the third law of, this is also known as the third law of the Faraday's law, or it is the another name is the Lenz law. Lenz law states that the cause opposes every cause of producing it. What does it mean? Lenz law states that the direction of induced EMF drives current around a wire loop to always oppose the change in magnetic flux that causes the EMF. If this is the south pole and if this is the north pole and the current is flowing from north pole to south pole, it will induce some EMF, and direction of EMF is always the opposite to the direction of the current. The direction of induced EMF drives the current around the loop, which is always in the opposite direction of the magnetic flux. That's why Lenz law states that the cause opposites of every cause of producing it. So we can write E equals to minus N d phi by dt. d phi by dt means the rate of change of flux it causes the generation of EMF or induction of EMF. So the direction is in the negative direction. Next one question is write the Maxwell's fourth equations. And this fourth equation is in the time varying field. It is not mentioned here, but the full question should be write the Maxwell's fourth equation in the time varying field. So from the Gauss law, this is the Gauss law of electromagnetic field or magnetic field. We can write the magnetic field phi is, we are using the bold letter to tell it is a vector quantity. Phi is equal to integration of b ds. And from the previous section we got what we got, E is equal to minus d phi by dt when number of turns n is equal to 1. Number of turns is equal to 1. Now if we substitute the value of phi here, we can get minus d integration of b ds by dt. One thing in the Gauss law for magnetic field, it is not like unlike the Gauss law, electrostatic Gauss law, it is not a closed loop thing. So we can write only surface integral. Do not write the closed loop integral. This is wrong. Closed loop integration is only for the electrostatic field. For the electromagnetic field, we will write only integration of S B ds. So what is the electric potential we know? We know from the first chapter electric potential E or EMF E is equal to integration of E dl. E is the intensity into dl is the length. So if we compare the both equation, here we got E is equal to minus integration of b ds by dt. Here we got E is equal to E dl. So comparing the both, we are getting integration of E dl is equal to minus integration of db ds by dt. We got minus db ds by dt. Here we can write surface integral of db ds by dt. So we can see now one side we are getting the ds, another side we are getting to dl. So we, for making them equate, we have to make both side either dl or ds. So here we are using the Stokes theorem. We know for increasing the one limit, one range, we can use the Stokes theorem. So E dl can be write as the surface integration of grad cross E into ds according to the Stokes theorem. So grad cross E is equal to integration of db ds by dt. Now you can see both sides as the surface integral. So if we equate the both side, we will get grad cross E is equal to minus db by dt. So this is known as the Maxwell's fourth equation or vector form of the Faraday's law. The question may come in the both language, write the Maxwell's fourth equation or write the vector form of Faraday's law. Next, state the Gauss law. We know this is the if Gauss law is given. We know we have already discussed many times in unit 1. Just one quick revision. The electric flux passing through any closed surface is equal to the total charge enclosed by the surface. So we can write psi, the total number of electric flux, is equal to ds. What is ds? ds is the surface area into ds is equal to charge enclosed q. Now, if we want to write the same formula for the magnetic field, what will be the formula? The flux phi is equal to integration of B, the magnetic field density, into ds. So, the same formula we can write for this is for the magnetic field. This is for the magnetic field, and this is the original or conventional Gauss law. It is for the electric field. Psi is equal to surface integration of ds dot ds. So this is the surface charge enclosed is equal to ds is the electric charge density into ds is the surface area. Next, name types of the EMF induced in the coil. We know if there is a rate of change of flux, we can get some EMF. So EMF is, what are the types of the EMF? EMF is basically two types. One is known as the statically changing EMF and another one is known as the dynamically changing EMF. First, we will discuss about the statically changing EMF. So, what is EMF? Induced EMF we get from the Faraday's law. What is the Faraday's law? E equals to minus n d phi by dt. So, EMF is two types. One is the statically induced EMF. What is the statically induced EMF? In the statically induced EMF, conductors are stationary and the flux is variable. Means we can think here that the flux we are changing the flux by moving the flux, but the conductors are stationary. We are getting the conductors is not changing any more. So flux, what is the example of this? The main example of this is the transformer. That's why the static EMF is also known as the static EMF is also known as the transformer EMF. The another name of the statically induced EMF is known as the transformer EMF. In the transformer, we know there are two coils, primary coils and secondary coils, and these two coils are static. Transformer is a static device. When we are giving the current, the AC current, it will create some time varying field, and as a result, the flux is also changing, and as the flux is changing but the field is stationary, it is known as the statically induced EMF. So unlike this, what is the another one? Another one is the dynamically induced EMF. So where we can, what is the change? Conductors are rotating and flux is constant. What is the meaning of the dynamically changing EMF? That conductors are rotating and flux is constant. And from where we can get this one? We can get the example of any type of generator. In the case of the generator, what will happen? In the case of the generator, we can see that there are some stators are here, and in the stator we will get some electric lines of force. Now if we take one armature and we will rotate the armature using any prime mover, it will induce the EMF in the armature coil, and this is known as the dynamically induced EMF. Conductors are rotating and flux is constant, and what we can also call this generator is also known as the generator EMF. So induced EMF is basically two types. One is called the statically or transformer EMF. Another one is known as the dynamically or generated EMF, and another name of this EMF is known as the motion EMF. So it is also known as the motion EMF. So these are the types of the EMF. EMF is basically induced EMF two types. One is the statically induced, one is the dynamically induced. Dynamically induced means conductors are rotating and flux is constant. This is known as the generator EMF or motion EMF. Statical EMF means conductors are stationary and flux is rotating. So it is known as the transformer EMF or static EMF. So what is define the dynamically induced EMF? In order to generate a dynamically induced EMF, the magnetic field must be kept stationary and the flux is moving. So we can tell in the process the conductor cuts the magnetic field and EMF is induced in the coil. So in this case, we can write the electric potential E is equal to BLV sin theta. What is the example? Example is motor. What is the already we have told that according to the definition, the EMF magnetic field must be kept stationary and the flux, not flux actually, field is the conductors are rotating. We should write here conductors are rotating. The language is little mistake. So the magnetic field becomes stationary and conductors are rotating. Already we have discussed in the previous slides. Conductors and rotating and flux is constant. So we are getting this definition. So in this process, the conductors cuts across the magnetic field and EMF is induced in the coil. And what is the value of the EMF? EMF is equal to E BVL sin theta. And what is the example? The example is motor. Now define the statically induced EMF. In order to generate induced EMF, magnetic field so what is the expression for the magnetic? So this is the first thing is the if the field is moving, we can tell this is the statically induced EMF, and statically induced EMF we can write E is equal to n phi m omega cos omega t. And what is the example? Example is transformer. Write the maximum value of dynamically induced EMF. We have to calculate the maximum value of dynamically induced EMF. So see, this is a motor we can think, and we are giving this is the conductor. This box is a conductor. So when current is flowing, it will induce some flux, and the maximum value of the potential induced in it is equal to, we know what is the maximum value? E is equal to BVL. We can write E, actually E is equal to BVL sin theta. When these fields are in the parallel to the conductor, what will happen? When the field is parallel to this conductor means the conductors, this is the field and the conductors, I will use another color. And you can see the red one is the conductor. Conductor current I is the conductor. So conductor is parallel with the field. So theta is equal to 0. So what is the value of EMF? BVL sin 0 means it is 0. But when the conductor is at the 90-degree angle with this is the conductor. When the conductor is in the 90-degree angle with the B, we can write theta is equal to 90 degree. So what is E? E is equal to BVL sin 90 degree. So we can write this is the E is equal to BVL. E is equal to BVL. So the maximum value of the dynamically induced EMF E is equal to BVL. What is the meaning of B? B is known as the flux density. What is B? B is the velocity of the coil. Velocity of the coil. And what is L? L is the length of the coil. And it the induced EMF direction we can get from the Faraday's Fleming's right hand rule. We can get the direction of E using the Fleming's right hand rule. What is the Fleming's right hand rule? If we keep the three fingers 90 degree apart from each other, if the current in the coil is given by the first finger and flux density with this, the direction of the coil will be in the thumb. Next, what is the statically induced EMF? Statically induced EMF means in the definition we got that the flux is moving but the coils are the field is moving but the conductors are stationary. So conductor experience a variable flux, then EMF is induced. What will happen? The conductor are fixed. Example is transformer. So conductor is fixed and it is experiencing some induced variable flux. So we know E is equal to E dot dl is equal to n d phi dt. Now, what is the cause of the time varying flux? We know the cause of the time varying flux is the current I, and AC current equation we can write as Im sin omega t, and what it will generate the field or generate the flux phi. And what is the phi equation? Phi m sin omega t. Now if we put the value here, E is equal to n d phi m sin omega t. And what is the differentiation? N phi m omega cos omega t, or we can write n phi omega cos theta. Now when theta is equal to 0 degree, we can get cos 0 is equal to 1, and this is the maximum so we can get the maximum value of the current. Now next question, what is the conductor current density? So current density means the conduction current density depends on the two things. Conductor current density refers to the current flowing to the surface in the conduction band in the time t. Current density, current is basically three types. Already we have discussed in unit 2 that the current is basically three types. One is called the conduction current. Another one is known as the drift current. And another one is known as the displacement current. So what is the meaning of drift current? Drift current means, what is the meaning of drift current? When we are giving any potential, we are forcing the charges to flow. So this is the forced current. We are not taking it now. Basically, current is basically two types. One is called the conduction current. Another one is the displacement current. What is conduction current? Conduction current is known as the amount of current or charges flowing on the surface of a conductor. When there is a conductor, some current will flow at a time t. This current is known as the conductor current. So, if there is any conductor, it should have some resistance and some capacitance in it. If IR is the current through the resistance and IC is the current through the capacitance, what is the conductor current? Conductor current I is equal to IR plus IC. IR is the resistive current and IC is the current through the capacitor. And if we write it in the current density form, we can write J is equal to then JR by JC, where J is the conduction current. You can see here the blue one is the current through the IR, and this golden one I don't know you can see or not actually. This is the IC. IC is the current through the capacitor and J is equal to JR by JC. How we can get this? If we divide this equation in the, and this is the KCL obviously. So if we divide all the currents by the cross-sectional area A, I by A is equal to IR by A plus IC by A is equal to JR by JC. So this is known as the conduction current density, where JC is known as the displacement current density. Next question. Write the integral form of Faraday's EMF equation. What is the meaning of Faraday's EMF equation? Already we got the integral form. Already we know what is the Faraday's equation. What is the Faraday's equation? Faraday's equation we know that E is equal to minus N d phi by dt. And also we have discussed the vector form of the Faraday's law, and in the vector form in the Faraday's law we got the equation grad square E minus dB by dt. It is known as the vector form of the Faraday's law, but this form is also known as the point form. What is the another name of this? The another name of this equation is the point form of the Faraday's law. Grad cross E is equal to minus dB by dt. Now we will discuss the integral form of the Faraday's EMF equation. So we are just changing it a little more, that grad cross A, and we are writing for the we can write it for the electromagnetic field. So grad cross H is equal to J plus d by dt. So what is H? H is known as the electromagnetic field intensity. Electromagnetic field intensity is equal to J. What is J? Already we have discussed in the last slide, but I will write it once. J is nothing but the current density. Current density plus D by capital D by dt. What is capital D? Capital D is nothing but the capital D is nothing but the electric flux density. Electric flux density. So we can write J is equal to sigma into E. Already we have discussed these things in unit 2. So what is sigma? Sigma is nothing but the conductivity of the material. Conductivity of the material. So we got sigma into E plus we can write d by dt is equal to j omega d naught. We have already discussed these things in unit 2. So sigma E is equal to j omega d naught. D naught is equal to, according to the Gauss law, d is equal to epsilon into E. What is epsilon? Epsilon into E. Epsilon is the permittivity of the medium. What is E? E is nothing but the field intensity. So if we take E common, we can get sigma plus j omega epsilon. So what is grad cross H? If we change according to the Stokes theorem, if we take integration in the both side, we can get H dl is equal to sigma plus j omega epsilon E into ds, and this is the integral form of the Faraday's equation. This is the integral form of the Faraday's equation. Integration of H dot dl sigma plus j omega epsilon E dot ds, or otherwise I can prove this also. So we can prove this also. We got grad cross H is equal to E sigma plus j omega epsilon. Already we got this equation. So what is grad cross H? We can multiply ds with both sides, dot ds, and we can multiplying ds in the both side. Now, if we take integration in the both side, we can take this integration for both. Now, if we use the Stokes theorem here, Stokes theorem, or we can tell inverse Stokes theorem here, we can write grad cross H dl if we want to change H dot dl. If we want to use the Stokes theorem here, we are just changing one label. So H dot dl is equal to sigma plus j omega epsilon, all are constant, E dot ds, and this is known as the integral form of Faraday's EMF equation. Next, what is self-inductance? Self-inductance is the property of the current carrying coil that resists or opposes the change of current flowing through it, and this occurs mainly due to the self-induced EMF in the coil. In this essence, the direction of the induced EMF is always opposite to the applied voltage if the current is increasing, and the induced EMF is in the same direction if the applied voltage is in the opposite direction. So this point is the main example of the Faraday's law for third equation, or Lenz law. The cause of the EMF is always, the induced EMF always oppose its cause. Here you can see that when current flows through and self-inductance, there is a rate of change of current which increase the voltage, or which can induce the voltage, and the direction of the voltage is always in the opposite direction. If current is increasing, the induced EMF in the opposite direction. What is mutual inductance? Mutual inductance is the main operating principle of the generators, motors, and transformers. Any electrical device having the components that tend to interact with each other also follows the same principle. If we think about the example of the overhead line, we can see that the inductance of one coil will links the another coil. So this is the mutual inductance. The interaction is usually brought by the mutual inductance, and where the current flowing in one coil generates a voltage in the secondary coil. So the definition is when two coils are brought in proximity with each other, the magnetic field in one coil tends to link with the other coil. If this is a coil and this is a coil and current is flowing, so the flux generated in this coil will tend to link the other coil. This is the general tendency. This further leads to the generation of the voltage in the secondary coil. This property of the coil, which affects the change of the current and voltage in a secondary coil, is known as the mutual inductance. The property of a coil which affects the change in current and voltage in the secondary coil. If this is the primary and this is the secondary, if it affects the secondary coil, we can tell this is the mutual inductance. You can directly get this from this example. If this is one coil and if this is the another coil and current I is flowing through the first coil, you can see this red one is the flux, and this flux will cut the secondary coil. And if number of turns in the secondary coils is N2, we can write N2 phi 2 is directly proportional to the I1. And the proportionality constant is M21, where M21 is known as the mutual inductance. M21 means the mutual inductance of second coil due to the current of the first coil. Similarly, we can write if the current I2 is flowing in the secondary coil, we can write N1 phi 1 is directly proportional to I2. N1 phi 1 is equal to M1 to I2. What is M12? M12 means the mutual flux of the primary coil due to the current in the secondary. The mutual inductance of the primary coil or first coil due to the secondary coil. And if we can write M12 is equal to M21. Next, series connection of the inductor. If two inductors are connected in the same direction, we can write L1 plus L2 plus 2M. If they are in the opposite direction, if it is in the opposite direction, we can write, this is the not ending, this is the opposite direction, sorry. If the currents are in the, you can see this is the one direction, this is the another direction, L is equal to L1 plus L2 minus 2M. So, this is the series. So, today we have discussed some useful definitions and terminology from Unit 5. And thank you all.
Like, share and subscribe. Hit the bell icon for more updates.